Oscar Whiskey.
The controls of an aeroplane enable us to maneuver it accurately and safely under all normal conditions of flight. Control is achieved by moving hinged surfaces on the trailing edges of the tail and the wingtips, the elevator attached to the tailplane, the rudder to the fin, and the ailerons to the wingtips. All of them operated by the controls in the cabin. Moving the control column backwards and forwards raises and depresses the elevator. Pulling it back raises the elevator, pushing it forwards depresses it. Turning the wheel operates the ailerons at the wingtips. With the wheel to the right-hand aileron is raised and the one on the left depressed, rolling the aeroplane to the right. Turning it in the opposite direction moves the ailerons in the opposite sense and rolls the aeroplane to the left. The rudder is controlled by pedals. Pushing the left-hand pedal swings the rudder to the left. Pushing the right-hand pedal swings it to the right. Each control can be operated separately, or they can all be used in coordination when the maneuver demands it. In the smoke tunnel, we can see how they produce their desired effect by deflecting the airflow. When we depress the elevator, the airflow is deflected downwards, and this increases lift on the tail. When we raise it, the airflow is deflected upwards, and the tail receives a download. The effect is to rotate the aeroplane around its lateral axis. The rudder works in just the same way in the vertical plane, with the airflow deflected to the right or left, so as to push the tail in the opposite direction, swinging the aeroplane around its vertical axis. The ailerons deflect the airflow in the same way but in opposition to one another, depressing one wingtip and raising the other at the same time, controlling the aeroplane around its longitudinal axis. The remaining primary control is the throttle, which enables the pilot to control thrust. To increase power, the throttle is pushed forward. To reduce power, it is pulled back. Let's see what happens when we use the controls to change the flight path, or simply to take off and climb. The pilot opens the throttle and the aeroplane accelerates. As flying speed is reached, he pulls the control column back, the elevator rises, the tail goes down, the aeroplane lifts off and rotates into the climb. The elevator returns to the neutral position. What the pilot has done is to increase the angle of attack so as to give the wing the extra lift it needs as the aeroplane rotates. Now let's look at the whole sequence in animation. The aeroplane accelerates to flying speed. The four forces are now in play. To rotate the aeroplane, we must put a download on the tailplane by raising the elevator. The angle of attack on the wing increases as the tail goes down, and lift becomes greater than weight. Once established in the climb, the elevator returns to neutral, lift is reduced to balance the component of weight acting at right angles to the flight path, and thrust must be increased to balance aerodynamic drag plus the component of weight acting backwards down the flight path. So the controls are used in this case to change the flight path from level to climbing flight. by a controlled increase in lift at rotation. To level off, the elevator is used in the opposite sense, to lift the tail. And thrust must be reduced to allow the aeroplane to remain at a speed where lift exactly equals weight. To descend, the elevator is again depressed and the tail lifts. And thrust must again be reduced to take account of weight acting forwards down the flight path. At the controls themselves, only very slight movements are required to deflect the control surfaces sufficiently to change the angle of attack and thus increase or decrease the amount of lift from the wings relative to weight, while the throttle is used to maintain the balance of thrust and drag. Going round corners, racing cars depend on their road-holding capabilities to prevent them being hurled outwards off the track by centrifugal force. If we try to turn an aeroplane with rudder alone while keeping the wings level, centrifugal force will cause it to skid sideways. On a bicycle, centrifugal force would throw us off unless we counteract it by leaning inwards towards the center of the turn. And so we bank the bicycle in the direction we want to go. We need turn the handlebars only slightly in the direction of the turn. So it is with the aeroplane. Here it is lift that provides the principal turning force. We've only to bank the aeroplane slightly in the desired direction, and even a small proportion of lift acting towards the center of the turn is powerful enough to pull the aeroplane in that direction. This means that lift has a double role to play in the turn. As we bank into the turn, lift acts partly into the center of the turn to counter centrifugal force, and partly vertically upwards to balance weight. The aeroplane turns. If we increase the angle of bank to make a steeper turn, a higher proportion of lift acts towards the center of the turn, and the proportion of lift still acting vertically is no longer enough to balance weight. So we must increase the sum total of lift. First by tightening the turn and so increasing the angle of attack. But this will also increase drag, so to balance it we must increase thrust. Lift and weight are now in balance. And so to control the aeroplane in the turn, the pilot first applies aileron and a little rudder. In a steep turn, the pilot increases the angle of attack by gradually pulling back on the control column and opening the throttle to increase thrust, so that the vertical component of lift still equals weight. Then when we come out of the turn, we reduce both angle of attack and thrust to their normal values in straight and level flight. We can turn in a glide. Or we can turn in a climb, so long as we use the controls to give the aeroplane the extra lift it needs in the turn. The twin-engined aeroplane differs from the single-engined in several significant ways. The most important aerodynamically is the way in which thrust is usually divided by mounting the engines on the leading edges of the wings on either side of the fuselage. This has the effect of directing the slipstream of each propeller over the wing itself, thus augmenting lift over a considerable proportion of its span. This means that the pilot can use the throttles to accelerate air over part of the wing and thus increase lift, controlling the attitude of the aeroplane in pitch and changing or maintaining height with very little variation in speed. However, there's always the possibility that an engine may fail. When this happens, total thrust and slipstream are lost on the affected side. Unless we prevent it, the aeroplane will yaw towards the dead engine. And the wing, having lost some of its lift, and now slowing down in the yaw, will drop. To straighten up the aeroplane and restore lift to the affected wing, the pilot must apply rudder against the good engine and hold it there until he can make a safe landing. To do this, he needs help. The way in which a displaced control surface can be held in position against a considerable aerodynamic force is by means of trim tabs. These are auxiliary surfaces fitted to the trailing edge of a main control surface and working in the opposite sense. Thus, a rudder trim tab applied to the right will hold the rudder to the left and vice versa. Trim tabs enable the pilot to correct and hold any normal variation in the trim of the aeroplane without having to hold the control force physically. Elevator trim tabs enable the pilot to trim the aeroplane in the pitching plane, and these work in the same way as the rudder tabs. Downwards to raise the elevator, upwards to depress it. These can be used to correct variations in the position of the center of gravity. The total weight of an aeroplane acts through a single point known as the center of gravity. The designer tries to put the center of gravity a little way ahead of the center of lift of the aeroplane so as to give the pilot better control. This is compensated for by fixing the tailplane at a lower angle of incidence than that of the wings so as to give it a download. But the loading of the aeroplane can change this relationship. An extra load placed behind the center of gravity will move it back to a point only just ahead of the center of lift. The aeroplane will now tend to pitch nose up. So we must trim the elevator to reduce the download and bring the aeroplane back to level flight. The aeroplane can thus maintain level flight despite the fact that the center of gravity is misplaced, provided it's still within the design limits of the aeroplane, and without the pilot having to hold the aeroplane level manually. In the same way, if we need to increase the download on the tail, we can use the trimmer in the opposite sense. The controls give us command of the aeroplane. They allow us to use the forces acting on it, to balance them as we choose, and to control the pressure pattern around the wings as they move through the air, so that we can fly and enjoy the aeroplane to the limits of its performance.